Hi, this is Professor Sartor, and I'm going to be working on a few problems related to exponential and logarithmic functions. This example says, write the logarithmic equation as an exponential equation. We have natural log z equals 3. Now, anytime we want to write a log equation as an exponential equation, we need to know the relationship between those two. So when we have a log, logs are always written as log base b of x equals y. And if we want to write that as an exponential equation, we're going to use the base of the log as the base of the exponent. Then the log always equals the exponent. So this log equals y, and we're going to put y in the exponent. And then this exponential will equal what's inside the log. So since we have x inside the log, that's what our exponential equals. Now, the example we have says natural log z equals 3. This is a special kind of log. It has special notation, and that is ln, which stands for natural log. And the natural log is just a regular log, but with the natural base. And the natural base is e. That's approximately 2.718. So essentially, when we use the symbols ln, that's the same thing as using the symbols log base e. So going back to our example, we have natural log z equals 3. I'm going to make sure that I think of natural log z as log base e of z equals 3. Now I'll rewrite this as an exponential. I'm going to use the base of the log as the base of the exponent. The log always equals the exponent, so 3 goes in the exponent. And then my exponential is going to equal what's inside the log. So since z is inside the log, z is what the exponential equals. So to write the logarithmic equation, natural log z equals 3, as an exponential, that would be e to the 3 equals z. This question says, evaluate the expression without the use of a calculator. ln, which is natural log, 7th root of e squared. All right, so let me rewrite the problem. And what I want to do is I want to simplify this portion that is inside the log. I want to write the radical in exponential notation. So having the 7th root is the same thing as having a 1/7 power. I guess I could take that a little bit slower. So having the 7th root is the same thing as the 1/7 power. We can multiply those powers using the power rule to make that 2/7. And when I want to simplify a log, I want to write it in exponential form because I understand exponential form a little bit better. I'm more comfortable with it. So I need to know what the base of this log is. Now these symbols, ln, are natural log, and those symbols are only used when you're using a base e. So that's the same thing. Natural log is the same thing as log base e. So I'm going to say I don't know what this expression equals. So let me call it p. I'm going to rewrite it as an exponential so that I can figure out what that p equals. So as an exponential, I would use this base of e. The log always equals the exponent. And the exponential always equals what's inside the log. So what's inside the log is e to the 2/7. So now I can try to figure out what that power is, that p. So on the left side I've got e to the p, and on the right side I've got e to the 2/7. So that must mean that p is equal to 2/7. The next question says find the domain of the logarithmic function. F of x equals log of -4 minus 9x. So the domain of logarithmic functions is going to be found with the idea that you can only take the log of positive values. So let me explain that in a little bit more detail. Let's say I try to find the log base 2 of -2. I'm not sure what this is going to equal, so I say it's equal to p, and then I'm going to rewrite this as an exponential. I've got a base of 2, so my exponent would have a base of 2. The log always equals the exponent, so I have an exponent of p. And then this exponential is going to equal what's inside the log. So -2 is inside the log, that's what my exponential equals. And when I think about 2 to the p equals -2, you realize that this is something that can never happen. You can't take a positive number and raise it to a power and get a negative answer. It just doesn't work. So we cannot take the log of negative numbers. We also can't take the log of 0. We have log base 2 of 0. I'm not sure what that equals. Let's rewrite it as an exponential to give us 2 to a power equals 0. We know that we can't take a positive number and raise it to a power and get an answer of 0. So logs are undefined for negative values and for 0. They're only defined for positive values. So when we're looking for the domain of a log, we're going to take what is inside the log, whatever expression is inside the log, and make that greater than 0, because greater than 0 are positive values. So let's take -4 minus 9x. That's the expression inside the log. We want that to be greater than 0, and we're going to solve. Add 4 to both sides. Divide by -9. This is an inequality. And when I divide by a negative with an inequality, I need to reverse the direction of the sign. So that becomes x is less than -4/9. We want to write our answer in interval notation. So think about this on the number line. You've got -4/9, which I'd mark with an open circle. And I'm going to shade the values that are less than that. So in interval notation, that shaded region would start at -infinity on the lower end. It would stop at 4/9 on the upper end. And I'm going to use a parenthesis to indicate that -4/9 is not included in the domain. This question says, use the product rule to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expression. So let's talk about what the product rule is. The product rule is something that we use for logarithms to rewrite them, either expanding them or condensing them. So with the product rule, the reason why it's called the product rule is because inside the log you're going to have a product. So I'm writing the product of m times n. This can be rewritten as log base b of m. Notice I'm using the same base that was originally given. Log base b of m plus log base b of n. Once again, using the same base. So because I have a product, I can write this as the sum of two individual logs. The first factor is inside the first log, the second factor is inside the second log. So for our example, we have log base b of 6 of p times q. So inside the log we have a product, that's why we're using the product rule. We can write this as log base 6 of the first factor, log base 6 of the second factor, and we're going to add those two logs together. This question says, use the quotient rule to expand the logarithmic expression. Whenever possible, evaluate logarithmic expressions. This log says log base 6 of 7 over p. So we want to use the quotient rule. The quotient rule is when you have a log base b, and inside the log you have a quotient or division. So we're going to have m over n. When you have the quotient rule, you're going to write a log for the value that is in the numerator and a log for the value that's in the denominator. And you notice that I'm using the same base that was given in the original, but we're going to use a subtraction sign on the log that comes from the denominator. So in our example, we have log base 6 of 7 over p. We will expand that to log base 6 of the numerator and log base 6 of the denominator and put a subtraction in front of the log base 6 of p, because that p is coming from the denominator. Whenever you finish expanding or using that quotient rule, you want to try to simplify the logs that you have. So in this example, the second log is log of a variable. We're not going to be able to simplify that. The first one is log of a number. Anytime you have log of a number, you should try to simplify it. In this case, because 7 is not a power of 6, we can't simplify that without using a calculator. So that's going to be our final answer, log base 6 of 7 minus log base 6 of p. This example says use the power rule to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expressions. So let's start off by talking about what the power rule is. The power rule is when you have a log base b, and inside your log you have something raised to a power. Let's say m to the power p. And when you have something raised to a power, what you can do is take that power and multiply it by the log that you have. You notice that the power is now gone from the m, and it's moved to the front of the log. It's multiplied by the front of the log. So in our example, we have log base 4 of p to the 8. So notice that inside the log we have p to the 8th, something to a power. So applying the power rule, we're going to take that 8 and multiply it times the log. And that's our answer, 8 log base 4 of p. This example says use the properties of logarithms to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expressions. So the properties of logarithms that we're talking about are these three properties: the product, the quotient, and the power rule. So they're given these names because inside the log we have a product or multiplication, quotient or division, and finally something to a power. So how we handle each one of these situations is that when we have a product, we can write that as the sum of individual logs. When we have a quotient, we can write it as the difference of individual logs. And when we have a power, we can move that power to the front or multiply by that power. So in our example, we have natural log of a to the 5th, b to the 7th, divided by c to the 6th. So this example is going to use all of these properties. We have a to the 5th times b to the 7th, that's a product. Then we have a fraction divided by c to the 6th, that's the quotient. And then each one of these has a power. So we're going to use all three of these rules on this example. So we have natural log a to the 5th, b to the 7th, over c to the 6th. The first thing that I like to do is recognize the individual factors. So we have a factor of a to the 5th, a factor of b to the 7th, and a factor of c to the 6th. Because we have those three individual factors, when we expand, we're going to expand to three individual logs. So I'm going to have natural log for the first factor of a to the 5th, natural log for the second factor, b to the 7th, and natural log of c to the 6th. Now, what I'm doing on this step is actually using both the quotient rule and the product rule in the same step. So these factors that came from the numerator, these logs are going to be positive because in our product rule, the product turns into the sum. However, our factor that came from the denominator, notice the factor from the denominator is the factor that's negative here. So this c to the 6th is going to have a minus in front of it. So we've used both the product and the quotient rule to expand to this step. We're going to go one more step and use the power rule. Each one of these expressions inside the log have an exponent. So using the power rule, I'll bring the 5 in front, 5 multiplied by natural log A, 7 multiplied by natural log B, and 6 multiplied by natural log C. And since each one of these inside the log are variables, we're not going to be able to simplify anymore. So that's going to be our answer. 5 natural log A plus 7 natural log B minus 6 natural log C. This question says, use the properties of logarithms to rewrite the expression as a single logarithm. Whenever possible, evaluate the logarithmic expression. So the properties that we're talking about are the product rule. The product rule says that if you have a product inside the log, you can expand it to be the sum of the individual factors. Then we have the quotient rule. The quotient rule says when we have division inside the log, then we can write those as subtraction of those individual factors, the numerator and the denominator. And then we have the power rule. And the power rule deals with having a number to a power inside the log, and we can bring that power out. So in this question, we're starting out with an expanded form. If we take a look at what's given to us, we have log base b of a plus log base b of c. So we're starting out with an expression that's like this one right here, and we're trying to convert it to one like this, which is condensing to a single log. Notice in the directions it says rewrite it as a single logarithm. So what I notice in my problem is that I have a plus sign. Both logs have the same base, so I'm going to be able to condense it using the product rule. So I'm condensing to a single log base b, and because my first factor is a and my second factor is c, I'm going to multiply those two together. So to condense to a single log, I'm getting a times c, log base b of a times c. This question says, use the properties of logarithms to rewrite the expression as a single logarithm. Whenever possible, evaluate the logarithmic expression. So the properties that we're talking about are the product rule, quotient rule, and power rule. If we have a product inside the log, we can turn it into the sum of individual logs. If we have a quotient inside the log, we can turn it into the difference. And if we have a power, we can bring that power out front as multiplication. Now we're going the other way, starting with an expanded form working towards a condensed form, which is a single logarithm. We're trying to convert it to a single logarithm. So looking at my example, the example we're given is log base 5 of m equals log base 5 of n. We're allowed to condense to a single logarithm because they have the same base, and I notice a subtraction between these logs, and so I'm going to be using the quotient rule to condense. So this is going to become log base 5, the same log base 5 that's in both individual logs, and the number that goes in the numerator is m because that log is positive, and the number that goes in the denominator is n because that log is negative. So we have log base 5 of m over n as our answer. Log base 5 of m over n. This question says, use the properties of logarithms to rewrite the expression as a single logarithm. Wherever possible, evaluate the logarithmic expressions. So the properties that we're talking about, properties of logarithms, are the product, quotient, and power rule. The product can be turned into a sum, the quotient, subtraction, and when we have a power inside the log, the power can come out. Now this question is kind of going in reverse of those, starting out with an expanded log and making it condense to a single log. So if we have a sum of two individual logs, that's going to become a product inside the log. If we have a difference of logs, that's going to become a quotient. And if we have a number out front, that number out front can be moved to become the power inside the log. So let's take a look at the question that we have. We have natural log square root x minus 1/3 natural log x plus natural log 6th root of x. So when we start to try to condense this, the first thing we want to do is handle the power rule. If there are any numbers out front, we need to move those numbers out front to become powers. You're not able to use the product rule or the quotient rule when you have coefficients. You notice that none of the expressions I have next to the product rule or quotient rule have a coefficient on these numbers. So we have to take care of the power rule first. So the first thing I'm going to do is move that 1/3 power into the exponent. Okay. On the other two expressions, natural log square root x, I want to rewrite the square root as the 1/2 power, and I want to rewrite the 6th root as the 1/6 power. That makes all of the expressions in exponential form. So I've taken care of that power rule with the power out front. Okay, the power rule moved that 1/3 to the power. And I've also changed the radical square root to 1/2, the 6th root to 1/6. Now that I don't have any more coefficients on the logs, I can use the product and quotient rule to condense to a single log. All of these are natural logs, so that's the log I'll condense to. And inside that log, you're either going to have products or quotients, and sometimes you might have both. So we notice that this log and this log are both positive, but this log is negative. So the two logs that are positive are going to be multiplied and put in the numerator, and the log that's negative is going to go into the denominator. So that's using the product and the quotient rule at the same time. So we have natural log x to the 1/2 times x to the 1/6 over x to the 1/3. Now in this example, because all of our bases on these exponents are x, we're able to combine these together into a single factor. So we're now going to be using the product rule and the quotient rule, but this time it is the product and quotient rule for exponents. So the product rule for exponents says that if you have x to the n power times x to the m power, you're going to add those exponents. So for example, if you had x cubed times x squared, that's x to the 5th power. You're multiplying expressions with the same base, so you add those exponents together. The quotient rule for exponents is when you have x to the n over x to the m. So you're dividing expressions with the same base, so you're going to subtract those exponents. So that's what we're going to do with our example here. We have x to the 1/2 power times x to the 1/6 power. They have the same base and they're being multiplied, so we'll add those exponents together. Then we're dividing by x to the 1/3, and we'll subtract the 1/3. So let me erase this so I have some room to work. So now I'm going to combine these together. 1/2 plus 1/6 minus 1/3. I need to get a common denominator to add those together. The common denominator is going to be 6, so that becomes 3/6. 3/6 is the same thing as 1/2. And then minus 2/6. 2/6 is the same thing as 1/3. All the bases are the same. You can combine the numerators. 3 plus 1 is 4, minus 2 is 2, so I have 2/6, and that reduces down to 1/3.